next lecture will be performed by Miron Kursa. Miron holds a master degree in physics and PhD in computer science, works for Interdisciplinary Centre for Mathematical and Computational Modelling at the University of Warsaw, where he teaches data science. He is an expert in intelligent systems, data analysis, and computational modeling. His current research considers ensemble learning, automatic knowledge extraction, and stochastic modeling of complex phenomena. He had participated in many research projects in a wide range of disciplines, including bioinformatics, neurobiology, remote sensing, audio analysis, agriculture, power engineering, and air transport, and developed many novel algorithms and methods. His lecture is titled Mathematical Modelings of Neurochemical Signs of USV Emissions. Miron, the floor is yours.
Hello, can I be heard? Hello?
Yes.
Can you hear me? Okay. Yeah. So as you said, my talk will be about modeling how does vocalization happens. It's an extension of Adam's talk. Some methodological aspects of that. Of that research. So as said, the topic that we will be talking about are correlation networks. So this is basically this network called B in Adam's talk. So the context of morphine administration. So you can see like vertices connected to various neurochemicals in various compartments of the brain. And you also have these two drivers of this structure. So the fact that the morphine has been administered before, and we are going on a context of that, and also whether the rats are in the withdrawal states or not. And we have the effect that the USV emissions, that the count of them that is measured, and we can see that it's somewhat connected, but what does it really mean? I'll try to highlight this issue. So to talk about mechanism, it's important to talk about information, but if we talk about information, we actually talk about entropy. So a few words about entropy. We have all seen this picture. Like we have a container with two compartments. One is filled with gas, the other is filled with nothing, with vacuum. And then we open a slit in this boundary, and the gas flows to equilibrium. And we know that this happens because this is a less entropic state, and this is a more entropic state. And somewhat we know that the universe wants entropy to grow. So the time flows from up to down. And there is a thought experiment done by Maxwell, who thought that we could put a door here in this slit and make it to be operated by a daemon, which will work like that it will bounce off the particles that try to go from this chamber to this one, and open the slit for the particles that want to go the other way around. So with such a daemon operating, we'll have the spontaneous growth of, spontaneous decrease of entropy, because the gas will go to one part and the other will go back to being a vacuum. So there's a question like, can this work, and while this shouldn't work? So there was some dispute among physicists. So the Szilard gets probably the best explanation. So he just observed that daemon needs some information about particles to properly operate this slit. So he needs to know whether the particle goes left or right. So in this picture, the information is kind of a negative entropy. And this has been worked upon, and actually Landauer showed that it's all good from the energy perspective, because the computation that daemon needs actually has to be irreversible. So it also increases entropy of the daemon system. So this can be done in theory, and actually it has been done in Japan in 2010. A system like that is called Szilard engine, and it actually can reverse the flow of entropy using a computer that does some computations of the state of the system. So we know that entropy is physical stuff, and knowing from the statistical mechanics, we know that entropy is such a sum over all states of the system with probabilities that they occur. And if they are equiprobable, we have this logarithm of states formula that has been originally developed by Boltzmann. And later on, Shannon got the idea that we can replace those physical microstates with possible messages in some communication system, because he wanted to work in this area, and this way created a new field of information theory. Yes, so the Shannon entropy looks mathematically the same. So we can formulate this for a system with a LED bulb that can go green or violet. And the entropy of the system theoretically is logarithm of 2. So this is 0.693 nuts if we are using this natural entropy unit with natural logarithm, or 1 bit if we are using logarithm base 2. So we'll be using bits later on. And you can see a simulation with a system that switches this LED in a half-half probability, and we can see that it's actually pretty close to its theoretical throughput of 1 bit per message. And we can also simulate a system in which those violet LEDs appear less frequently. And this system also transfers entropy, so information, but at the much lower rate. So this is an observation that if we can predict something about the system, this makes it less informative. Because if we know something, we cannot be informed the same thing again. We can only learn what we haven't already known. So now the difference between physics and information comes from the extensivity. Right? If in physics, the states are independent, so the entropy adds to each other. Right? There is no correlation between gas in two balloons, so the entropy of the system of two balloons is just a sum of the entropies of each of the constituents. Yeah, and the same can be shown with a system of two bulbs, and here they are moving independently, so their joint states are also almost equally distributed. So their joint entropy, so the entropy of both systems taken together, is just a sum, and we can see that it validates in numbers in our simulation. But we can also have systems that are correlated, because if we need to have a system, it shouldn't be composed of parts that are just independently loosely working, because this is literally just a pile of parts, not a system. This is a more important case, and here the systems are perfectly correlated, so some joint states are totally impossible. And we can visualize how this works with two circles. There is an entropy of the first constituent, of the second. Here is the entropy of them joined together. So it's not a sum, it's something less. And this less is some kind of a common information in A and B. And here we can see that it works. We have perfect correlations of the entropies of all those three things are the same. And yes, this common information is called mutual information. It's marked with I. This is the obvious formula for that. And we can also have the other hand with conditioning, the conditioning in entropy. decreases information. So this is a question, how much information about A we have when we know the state of B. Like if the B is independent, this is the same thing, but if B is correlated with A, like we're losing something. I was basically just making some kind of crescent of this circle. So we can say that the joint entropy is the entropy of A minus B plus the mutual information plus the entropy of B knowing A. Yeah, so this is somewhat usual. And as I talk, the talk was supposed to be about correlation networks, but we are talking about some kind of mutual information. And why is that? It's because in like for normal variables in let's say popular continuous entropy framework, because we can have several extensions of information science over continuous variables, but I won't talk about this much. We have that there is a monotonic relation between the entropy or the mutual information, sorry, with the absolute value of correlation. Yes, and this actually doesn't work for 100% correlation, but like we can have a better framework in which this problem disappears. But it's generally okay to consider the absolute value of correlation to be a mutual information. So like doing standard Pearson correlation or Spearman one, which is actually like something about normalizing margins, or we can also use Kendall correlation. It's all the same things, and they map to mutual information equally well. And the last thing I want to say is a few words about is something called conditional mutual information. So it works like that. We want to know what is the mutual information between A and B if we know the state of C. On this formula is trivial to be created. And the interesting stuff here is that while conditioning always decreases entropy, like it does not work the same way on mutual information. Like it can decrease mutual information when there is some redundance. So when the information in C duplicates this that is shared between A and B. But this mutual information of A and B conditioned on C can be also larger. And this indicates synergy, that the information in C somewhat complements this shared between A and B. And this is the mechanism that allows us to like make multivariate interactions, because they are going here, and we can see that some multivariate interaction can increase something that is not visible on the bivariate one level. Yes, and actually there is interesting stuff that indeed all those mutual informations can be zero unless we plug some insanely large amount of conditioning inside. And this is why we cannot, in general case, inference any correlation between analyzing all the subsets of variables, which is pretty scary and which makes this probably senseless in the meaning of mathematics. But fortunately, those hardest interactions are also hardest to arise naturally, so they are mostly synthetic. So we can look what is the effect of on this network if we add all the synergic effects, all the multivariate effects. And so in this case, we're simulating them with a Borut algorithm, and what we can see here is that we get a total hairball that probably disables us to say anything meaningful about this network. So like those are cool methods, but they are not really for network inference. They are better to analyze what are individual vertices doing, not to look at such a gargantuic network. So yeah, I'll go back to this conditional mutual information. So we talked about this formula. It can be negative or positive, and actually it turns out that it's also independent of the order of variables. So this is some separate individuum, and this is actually the mutual information of three variables, which is positive for redundance, negative for synergy, and zero for independence. Yes, so we can talk how this work in practice. We can get a triangle of three systems that are correlated, and unfortunately we can see that there can be basically three mechanisms behind this structure. So we can have something called a collider when the two systems fed information to the third. Like we can have something called mediator when one system just relays information, and something called a confounder when there is one system that drives each of the other ones. So indeed, this mutual information of three elements can only allow us to distinguish this from the other two. But the thing that I want to stress here is that in this case, like the correlation network has added a spurious edge in each of these cases. So this shows us that the correlation network are not only too shallow, they are also too dense. There are edges there that shouldn't be there from the causal perspective. Not yes, that, as I said, that distinguishing these cases are tricky, especially when the estimation errors comes to the arena, and also when we have some latent vertices that we don't measure. And yes, this is an example of applying this triple mutual information framework to this network we have seen already. So these are the top most redundant vertices here. So what we can see here is nicely is that this is actually all the vertices from nuclear accumbens. So we can see that this structure has some high internal correlation, and the same applies to those three amino acid vertices in VTA. So we can see like structures that have some high internal synchronization, so maybe there are some kind of switches. And we can also see the most synergic vertices, so these that are more likely to participate in some kind of colliders, so actual processors of the information, so the most interesting places to put some interventions. And yeah, this is a kind of analysis that led us to the experiment with this emotional bending that Adam presented. And we also see that those two interventions that are underlying the experiments are also within these nodes, which like validates the idea. Yes, and also we have said that we can analyze the topologic parameters of the correlation network, for instance, with Pagerank, which measures which nodes are connected to more important nodes. So this is a recursive definition. And what we have seen here is that there is actually a significant correlation with both maximal, this triple mutual information for each node, as with this minimal one. So both the synergetic and redundancy effects are correlated with these topological parameters, but they bring this more resolution because like we have two variables, not just one. And so we can see here this nuclear accumbens cluster quite nicely. And here we have some crazy structures that actually are likely colliders, but they have low PageRanks, so they're probably parts of some interesting circuits here. So yes, but going back to the definitions, there's also one thing that it's nice to say about. This is something called data processing inequality, which happens in a mediated circuits. So this is what allows us to distinguish between a mediator and a confounder. Yes, and this says that the path from the start to the mediator has more information than the path from start to an end. So we know that mediator can at least destroy some information, or at least it can only retain information, and probably it will destroy something, but it cannot add anything, like not like a confounder. So the equality is, as I mentioned, 0 if the equality is reached only for this 0. So when the information is relied perfectly, and we can see an example of how this works. This is a translation of colors between English back to Polish and back to English. So this is a perfect system. We can say the same thing for Japanese, in which like green and blue can be translated to the same word, which is later translated back to blue. And this makes us lose the information about the green color altogether. So this is how digital systems lose information, and analog systems do this mostly the same, because they just intermix the similar information, because they are just indistinguishable given the noise in the system. And we can use this tool like to make also some inferences in the correlation networks. This is something I'm working on currently. So this Y node is the USV count in the same network as on the first slide. And here you can see only the mediated paths. So these are the paths in this network that are highly mediated and free of some injections of information from other sources. So we can see that the immediate neighborhood of the vocalization are those serotonin levels or its metabolites in certain probably nearby structures. So it reconstructs the original insight, but it also shows some larger circuits that probably can be identified and identified with some biological mechanisms. Especially, it's nice that it makes some longer circuits back to nucleus accumbens, which, as I said before, we believe is some kind of emotional switch, because it still goes back in various of our experiments with Adam. So yes, this will probably go out soon, so you could also use it. But now we're working on like a paper to identify what does it mean precisely. So this is probably the end of my talk, and the takeaways is that I hopefully have shown that information theory is something worth checking out, despite it's obviously scary math, but still it's pretty nice, and it glues various disciplines together. And about those correlation networks or those scary graphs, so we must remember that they are just diagrams of how information is shared between various systems, and they have limitations. As I said, they can have too little edges, because we can miss multivariate interactions, and they can also have too many edges, because information can leak from causal edges to non-causal ones. So interpreting correlation links in causal times is risky, at least. And yes, and some people will tell you that you can fit a bias network, which will show up all the causal interactions. But in my humble opinion, this is somewhat a lost cause, because the characteristics of the data, which are like wide and not particularly large, this mostly makes a situation like that you have many networks that fit the same data equally well. So you can fit one network, the other one, which will show different mechanism, and they will fit mostly the same. Yes, that's ignoring the fact that fitting bias networks is also very computationally expensive. So this requires HPC systems, and like this is why people usually don't see that it's also highly unstable. So my solutions to that is that we should rather look at some. So we should rather critically look at correlation networks that try to make those perfect ones, and try to make causal inference using some automatic insights combined with domain knowledge. And this is all I have for you today. So thank you for invitation for this great conference, and I'm ready to take some questions because I think there is some time left.
Yes, thank you, Miron, very much.